When architects start designing processor instructions, the first thing they worry about is how data should be moved from one place to another within the processor. Data copies between registers or register and memories are the most primitive instructions, and these are heavily used. Typically, first assembly program starts with move or copy instructions. It's like writing hello world program in C. Data copy is one aspect of data flow within the processor. Another important aspect is how it is getting transformed and what kind of arithmetic is happening on it. As shown in the diagram, these two aspects constitute the data flow within the processor. When we talk about data flow in the context of 8051 microcontroller, we are referring to data copies or all kinds of move instructions and arithmetic and logical instructions. We can put arithmetic instructions into four broad categories: addition and subtraction, multiplication and division, logical operations, and bit manipulations. As part of performing arithmetic, LU also keeps reading and writing program status word where various flags are manipulated. In this section, we will learn about all these instructions, one after another. Operands of an instruction may be accessed in many different ways. These mechanisms are referred as addressing modes. Basically, it is telling us how to access or address a particular operand of an instruction. 8051 has 5 different addressing modes. When one of the source operand is a constant, addressing mode is called immediate addressing. It is called immediate because the constant is part of the instruction itself. As we see in the example here, in the immediate addressing mode, we should put hash before the constant. Otherwise, it is considered an address. In the first example, constant 32H is being copied into register R2. Similarly, in the other instruction, value 0EH is being copied into accumulator. Further, in immediate addressing, depending on the target, constant can be 1 byte or 2 bytes. In register addressing, both source and destination are registers. In this case, both operands are referred as their register names. Further, in arithmetic instructions such as sub B or add instruction as shown here, destination is always accumulator. In direct addressing, one of the operand is a memory location, and the complete address of this location is part of the instruction. Note that there is no hash before the constant. If we put hash, the constant would be treated like an immediate value. In the first example, value at address 31H is being copied to accumulator. In the second example, accumulator value is being stored at location 02H. Another addressing mode is register indirect addressing. As the name suggests, in this case, address is there in some register. In 8051, only register R0 and R1 can hold an address value. In the assembly, @ must be put before one of these registers to tell that address is actually there in the registers. In the first example here, value stored in the address pointed by register R0 is being copied to accumulator. Another addressing mode is index addressing. In this case, base address is there in DPTR register. Actual address is calculated by adding offset present in the accumulator A with the base address. This is the reason this kind of addressing is called indexed. Offset is nothing but the index. With this background, let us learn more about the accumulator before going through various data flow instructions. Accumulator is a special register used by arithmetic logic unit. It is referred as register A, and this is the destination of most of the byte arithmetic and logical instructions. For example, addition instruction or subtraction instruction or multiplication. So all these instructions have destination as accumulator. This register accumulates result That is why it is called accumulator. Multiplication and division are performed on registers A and B. This is because when two 8-bit numbers are getting multiplied, they have to be put in 16-bit register. Similarly, when one number is getting divided by another number, there will be quotient and there will be remainder, and they will go to two different registers. That is why we need two registers here, A and B. We will go through these instructions later on. For now, let us just understand the utility of accumulator. One important point to note is that making destination implicit makes it possible to have 1 byte encoding for register addition instruction. This saves program memory. For example, for an instruction add a rn, first 5 bits indicate that it is an add and destination is A. Last 3 bits are the exact source register encoding. That is how entire instruction fits into 1 byte. Now let us look at all copy instructions next. We discussed earlier that data copies are the most basic instructions of the processor, and they make foundation of data flow within the processor. 8051 supports various flavors of copies. Let's go over all of them one by one. So the first one is copying a constant to a register. So here we show two examples where in the first example an immediate value 32H is being copied to register R2. In the second example, an immediate value 0EH is being copied to accumulator. So the first operand of this instruction will be a register, and the second one will be the immediate value. The second flavor of copy is copy register value to another register. So here we are showing two different examples where in the first example, the value of register R0 is being copied to accumulator. In the second example, the value of register A is being copied to register R2. So in these instructions, both the operands will be register values. And as you can guess here, this instruction is going to be 1 byte instruction. Since there is no immediate value, the entire instruction can fit into 1 byte. Another possibility of copy is copy to or from a direct memory location. In the examples here, in the first one, there is address 31H, and therefrom the value is being copied to accumulator. This is also called loading the memory value into the register. In the second example, the value present in accumulator is being copied to address location 02H, and this is nothing but storing the value in the memory location. So the first one can be thought of as load, and the second one as store. Another copy instruction is from indirect memory location. So in this case, the address value is there inside one of the registers. So in the example shown here, in the first one, the address is there in register R0, and the value at that address is being copied to accumulator. Similarly, in the other case, the value stored in register B is being copied to the memory location, address of which is there inside register R1. Another copy instructions are copy to or from index memory location. So in the example here, the base address is there in DPTR register and the offset is there in accumulator. And the value present at that particular location when we add base address with the offset is being copied to accumulator back. The last one is bit level copying, and the syntax is pretty simple here, as you can see. So in this case, P2.3 means that the third bit of port 2 is being copied to carry flag. As we see here, in a bit level copy instruction, a specific bit of a particular register can be referred directly. As we discussed earlier that as part of executing various instructions, LU reads program status word or PSW register and also keeps modifying it depending on the result. PSW indicates the status of arithmetic result with carry, auxiliary carry and parity flags. It further shows error condition with overflow flag. Bits RS1 and RS2 help in selecting one of the register banks. PSW is further read by most of the jump instructions to decide the correct branch. Now let us take a closer look. The most significant bit is for carry flag. It indicates overflow in case of addition and borrow in case of subtraction. Next bit is auxiliary carry or AC flag. This flag is used in binary coded decimal or BCD arithmetic. We will see these operations in coming lessons. F0 or flag 0 as it is called is available to the user and it has no pre-specified functionality. RS1 and RS0 bits indicate register bank. Value 00 means bank 0 and 11 means bank 3. We have already seen the banks in the memory organization. OV flag indicates error conditions such as divide by 0 or overflow in case of signed arithmetic. And the LSB is for parity flag, which indicates the parity of value stored in the accumulator register. Let us go over various addition instructions in 8051. There are two flavors of addition instructions. The first one is addition without carry. In this case, the numbers will be added, and with these numbers, carry will not be added. So we have an example here where we are trying to add two numbers. The first one is 32H and the second one is 0EH. So in this case, result is 46H, and as happens in all the arithmetic instruction, result is there in accumulator. In this case, carry flag is 0. This is because there is no carry from bit 7. But there was a carry from bit 3. So in that case, auxiliary carry flag will be set. And further, there are three ones and the result will have the parity flag as 1. The parity flag is 1 because it's even parity. And you just add 1 to all the ones in the accumulator and the number becomes even. So it's even parity. The other flavor of addition is addition with carry. Mnemonic for this is add C. This must be used when we are adding multi-byte numbers. We have an example here where we are trying to add two 2-byte numbers. And in this case, when we add the first byte, there is a carry from the lower byte. And if we don't use add C instruction in this case, then the result will be incorrect because there was a carry from the lower byte. Another important flag with addition is overflow flag. And that makes sense when the signed numbers are being added. So overflow flag will be set in two different conditions. So in the first case, suppose there is carry out of bit 7, but there is no carry out of bit 6. Then the overflow flag will be set. In the other case, suppose there is carry out of bit 6, but there is no carry out of bit 7. Then again the overflow flag will be set. So the first one belongs to overflow in case of negative numbers, and the second one belongs to overflow in case of positive number. So the example we have here, in this case, overflow flag will be 1. Another important addition corresponds to BCD addition. BCD stands for binary coded decimal. As you would have noticed in all the examples that the value inside register is pure binary value. And if you consider the 4 bits, the lower 4 bits or upper 4 bits, as we are writing in hexadecimal format, the value can range from 0 to F. In decimal sense, they can range from 0 to 15. So that is a binary representation. But there are many applications where you have to represent the number in decimal format. For example, your displays. So in displays, if you start displaying the number in hexadecimal form, people will get confused because hexadecimal form is not used in the normal life. The people will not be able to comprehend that. So in those applications, we want to display the number in decimal format. So that is why it makes sense that whenever the addition has been done, if we can somehow convert that into proper decimal format, then it will become suitable for display in the decimal format. So let's go over it. So BCD numbers can be represented in two different ways. The first way is unpacked BCD. So in this case, what happens that the BCD number such as 4848. So in this case, the number will be stored in two different bytes. First digit will be stored in the first byte, and the other decimal digit 8 will be stored in the other byte. On the other hand, in case of packed BCD, both the decimal digits will be there in a single byte. So upper nibble that will correspond to first decimal digit, and lower nibble will correspond to second decimal digit. So when we add two packed BCDs, as we show here, we have two numbers 48 and 89, and the result is 137. But after applying addition, the result in accumulator is not 137, it's actually D1H, and there was a auxiliary carry flag. So the lower nibble is not 7, it's actually 1, and that is because the nibble had the range from 0 to 15, not from 0 to 9. So basically there is sort of overflow and we have to adjust it. And to adjust that, we should add 06H. And once we do that, then we get the right lower nibble number. Similarly, in this case, the result is more than 100. So we have to adjust that also. To make all these adjustments, there is special instruction inside 8051 that is called decimal adjust or DA. So whenever we are doing BCD addition, we should have this instruction as well. So that is why this DAA has been put in the example. And once we do that, then we get the correct value. So C becomes 1. That indicates that the number value is more than 100. Accumulator value is 37H, which is the correct one. And the final result is 137. So in case of BCD addition, overflow flag is not affected. 8051 has only one subtraction instruction, subtract with borrow, and its mnemonic is sub B. In this case, borrows comes from the carry flag. Suppose we have an instruction sub B A comma R2, and that would be equivalent to A equal to A minus R2 minus C. Setting of flags is similar to addition instruction. Carry flag becomes 1 if borrow is needed for bit 7, otherwise carry is 0. Auxiliary carry is 1 if borrow is needed for bit 3, otherwise AC equal to 0. Condition for overflow flag is also similar. When borrow is needed for bit 7 but not for bit 6. In the other case, when borrow is needed for bit 6 but not for bit 7. So in these two cases, overflow flag will be 1. In the example shown here, the numbers are such that it results in an overflow. You can also try this out in the lab. Let's move on to multiplication and division instructions now. For both multiplication and division, we require two registers. In 8051, it makes use of registers A and B for these operations. So let's look at multiplication first. The syntax is mul space AB, and in this case A will be multiplied with B. The result also goes into these two registers. The lower byte will be there in A and the higher byte will be there in B. Carry flag is always cleared, and if the result is more than 255, the overflow flag will be set. In the example here, we are moving 72H into A and 53H into B. And when we multiply them, the result is more than 255. Hence the overflow flag is set. Syntax of division is also similar to multiplication. It's div space AB. And in this case, A will be divided by B. Quotient goes to A and remainder goes to B. Carry flag will also be cleared. And if B is 0, in that case, it's going to be divided by 0. So overflow flag will be set. In the example here, we are moving 74H into A and 13H into B, and when we divide, Since it's not divided by 0, there's no overflow flag, and C is also cleared like multiplication operation, and results are there in A and B registers. Let's go over all the logical instructions. These instructions can be put in two different categories. The first category is that of binary instructions, and the second category is that of unary instruction. So binary instructions are AND, OR, and XOR instructions. Mnemonic of these instructions are ANL, ORL, and XRL. L stands for logical, and the first two letters indicate what kind of instruction it is. So ANL is AND logical, ORL is OR logical, and XRL is XOR logical. And the semantics is pretty clear. The target is accumulator, and the other operand is some source operand, and can be immediate value, or it can be register, or it can be memory location. And depending on whether it is register or immediate or memory location, it's going to be 1 byte instruction or 2 byte instruction. So unary instructions, the first one is clear, which actually resets the corresponding register. Next one is complement accumulator. It will complement the value within accumulator. Then we have swap instruction. So in case of swap instruction, the lower and upper nibbles will be exchanged. That means D7 to D4 bits, they will be moved to lower positions, and D3 to D0, they will be moved to upper positions. Then we have four different categories of rotate or shift instructions. R stands for rotate, L stands for left, and R stands for right. So if it is rotate left, then it is RL. If it also involves carry, then it is going to be RLC, and similarly mnemonic of rotate right can also be constructed. So basically it's going to be RR or RRC. And accumulator is the one which is involved in these instructions. So RL is rotate A left 1 bit position, and RLC is rotate A left through carry. As you can guess, in this case where the carry is also involved, the total number of bits involved in the shift will be 9. Where carry is not involved, then it's going to be only 8 bits. So we are not going to have a very detailed example of all these instructions over here, because these are simple logical instructions. I would suggest that you try all these instructions in the lab. 8051 has several instructions for bit level manipulation. It's a very powerful feature in 8051. Many MCUs don't have this feature. If you have to rely on byte level instructions to do bit manipulations, then it's going to be expensive in terms of number of instructions, which is going to take more memory space. And also it will incur performance penalty, because if there are more instructions, then it's going to take more time to execute them. So in 8051, bit level instructions are pretty handy. As you can see here, like other logical instructions, there are two categories of bit level instructions. The first one is binary instructions, then second one is unary instructions. So in binary instructions, you can perform bit by bit and or XOR kind of operation. Other binary instructions are copy instructions, like move C some particular bit. So in that case, carry flag will have the corresponding bit, or vice versa. So here bit can be a direct reference to a particular bit. For example, suppose you are referring to third bit of program status word, then you are going to write this as PSW.3, or it can be a bit addressable memory location. So in the memory organization, we saw that some memory location has been reserved for bit level manipulation, and you can actually write those addresses right here if you want to access memories directly. So let's go over all the unary instructions. So there is instruction set B, which actually does set bit. That means that particular bit will be set to 1. Then there is clear, which will set the value to 0. And then there is CLP instruction, or complement instruction. And there are two different flavors of these instructions. One is where it is directly addressable, and the other one is where you can put the memory location. So again, I'm not going to put different examples for all these instructions. Let us go over our first assembly program. The program starts with an org directive. Org is followed by an address. Org says that the following statements, which may be instructions or initialization of data, are placed starting from the given org address. So in the example here, all the instructions will be put starting from address 0. In this program, after org, we have a label main, which is the entry point of the program. We have a very simple program here. In this one, the accumulator is first initialized and then incremented in a loop. The first instruction after label main is to initialize the accumulator with 0 value. L1 is the entry point of the loop. The first instruction in the loop is to increment the accumulator. We have used add instruction here. We could have used some other instructions such as inc or increment. The next instruction is that of short unconditional jump. We will introduce sjmp instruction later on. For now, just assume that because of this execution, the CPU will jump back to the loop entry point. The program ends with end directive, which tells assembler that there are no more instructions to be processed. I will suggest that you try out this program in the lab to get a feel, and also go through other exercises which are discussed next. Let's go over a couple of assembly programming guidelines. The idea behind these guidelines is that once you have gone through them, you will be able to write a better assembly program, and the program will be more efficient and easy to read. One of the first things you can do is use symbols for recurring constants. So we have an example here on the right where we have defined a constant baud rate count, and this has been defined with the directive equ, which means equals. So in this case, baud rate count will be equal to -3, and this constant can be used to move into timer register th1, which is typically used to set up the baud rate while serial communication. So we don't have to worry about serial communication right now. This is just to give an example how a symbol should be defined for recurring constants. Further, we should also name labels appropriately to keep them meaningful. So on the right here we have an example where we are polling timer flag TF0. So the label here can be named as poll timer 0. So that's how we can make it more meaningful. It makes it easier to read. When the assembly program becomes quite large, one thing we can do is we can break the large code into subroutines. That will make it easier to maintain and read. Suppose we have to calculate factorial quite frequently in the program. So in that case, we can write a subroutine for factorial, and we can name it. We can name the label as routine factorial. Just be aware that if you are going to break the code into subroutines may have a small performance penalty, and specifically you should not be putting subroutine calls in the innermost loop, because if you do that, there you may have a large performance penalty. So apart from these, what else you can do is when you are initializing bytes in the memory, you can use db or define byte directive. So in this case, assembler will make sure that the appropriate code has been generated to initialize the memory, and in these cases explicit move instructions will not be required, so your program will be more efficient. So these are some of the assembly program guidelines, and if you follow these, your code will be easier to follow and read. Later on, we'll come back to more performance guidelines which will help you to improve the overall performance of the code.